distinguished academic and accomplished researcher, Dr. Muhammad Asad Zaighum, who is serving as an associate professor and head of Department of Mathematics and Statistics at Riphah International University Islamabad. He is one of the two Pakistani mathematicians to be published in the world-renowned Journal of Functional Analysis, a prestigious milestone that speaks to the depth and impact of his research. His academic journey began at COMSATS University Islamabad, where he earned his undergraduate degree in math with distinction as a part of 2005 to 2009 batch. Driven by a passion for deeper mathematical inquiry, he went on to pursue his PhD from the prestigious Abdus Salam School of Mathematical Sciences at Ghori College University Lahore. Dr. Zaighum's expertise lies in fascinating world of harmonic analysis, a field which is both deep and technically demanding. Beyond research, Dr. Zaighum actively contributes to academic administration, curriculum development, and the supervision of PhD scholars at his institution. His dedication to mentorship and academic excellence continues to inspire a new generation of researchers in Pakistan. Currently, he is expanding his academic horizons internationally as a visiting researcher at the Department of Mathematics, Nazarbayev University, Astana, Kazakhstan. When it comes to today, the focus of today's conversation is to introduce grand net spaces. Dr. Zaighum will discuss their basic and functional properties and will conclude by presenting a criteria for the boundedness of integral operators. Without further delay, I now invite Dr. Muhammad Asad Zaighum to deliver his talk.
Okay, thank you very much for a very nice introduction. Okay, can you hear me now?
Yes, sir.
Okay, okay. First of all, thank you very much for allowing me chance to speak at a place where I started learning mathematics. It was a place where I took this first step um, of becoming for choosing this career in mathematics. We'll start our presentation, but uh, to start up, I should like to tell you I did my BS during the period 2005 and 9, 2005 to 9. I joined in fall semester, and as you know, in the fall semester, many people students are looking to go to this engineering programs and things like that. Like other student, I also applied to some UET also, but on the other hand, I also applied for this BS mathematics because I had that particular interest about this mathematics. I still remember um, uh, on the orientation day. This was the same day at which some entrance exam was to be held at UET Texila. And I remember I spoke to my father and I told my father that, okay, he told me that, okay, maybe you can go and give this test and maybe later you can switch to, if you want, you can switch to this engineering thing. But I remember one day before I told my father that, I want to do this mathematics thing. And he fully supported me. And from that day onwards, I never looked back. I concentrated myself to mathematics and try to learn as much as possible. Try to dig deep, try to see difficult things, and try to do my best. Okay, let me share my uh, screen. Think. Okay. Oh, sorry. Okay. Can you see the slides?
No.
Can you see
Yes.
the slides?
Yes.
Okay. So I would like to talk about these grand function spaces, and I would like to tell you about the history, why these spaces are important, and some new development which is done in this direction, and some without any difficult proofs or anything else, just the basic ideas, just the things how these things are developed. So if we start with the title, if you look at this one, function spaces, to understand function space is like this. You have a set, and the sets consists of elements. If these elements are functions, so we call this a function space. But this space word comes from a structure. To start with, we consider the structure of vector space. So you have a set of functions, for example, functions real valued or complex valued, and you have a structure of vector space. For example, you have addition, scalar multiplication, and those properties with respect to addition and scalar multiplication. But in our study, we consider function space is a collection of functions equipped with not only vector space structure, but also the norm structure. So for us, a function space is a set which consists of functions, and it has a norm structure. Um, if you want to see or consider some example, you learn this example maybe in the first course of calculus. Uh, this collection, CAB, the class of all continuous functions on closed interval AB. So this is a set again. What are the elements of this? These are functions, and they have a vector space structure, and you can define the norm also. The norm can be defined by taking the supremum or the maximum because of a very nice theorem from real analysis. You can always compute this maximum on this one. So this is one easy example of the class of the function space. Another class would be, for example, differentiable functions. That is what you study in calculus, and it has a vector space structure. For example, if you add two differentiable functions, the sum is again differentiable. If you multiply a scalar with a function, then this function is again differentiable. And since it is, if you consider, not close, let us click open one. If you consider this relation, see, we know that every differentiable function is continuous. So you can define the same norm on it. So this is another easy example of functions space. All the sequence spaces, they are also function spaces because the sequence is in a special kind of a function. Why it's a special kind of a function? Because it consists of functions whose domain is the set of natural numbers. So all the sequence space and these guys are all here. Okay. So to tell you, this was my registration number when I was studying, and if you can see, this is uh, fall 05, and I still remember that many places I still use this number 022 because I want to remember these things for this for a long time. Okay, these are the outline of my presentation. We'll see the abstract, then we see Grand Lebesgue space. I will spend a bit of time here, and we'll define this one. And then this one is more technical, more research oriented, and we'll see some results here. Okay, so what is the abstract? So we'll see the motivation, the historical development for grand function spaces. We'll see what is grand function space, and this area is in what you say, in the sense of mathematics, is not so old. It's only what to say, 2 to 3 decades ago. This, in fact, it's 3 decades ago. These things were discovered. However, more emphasis has been made in last 2 decades around these spaces because they are being used to for application in many problems. So this is the first part. In the next part, we will study net space, and we will consider a thing which is called grand net space, and we will see the structural properties, some interpolation results, and we'll see that how this spaces extends the grand Lorentz space. So you will see this interpolation thing. Maybe you might have seen this interpolation thing in numerical analysis. But for example, in harmonic analysis, we do have this interpolation. But now this interpolation is between two Banach function space. And then there are methods how to compute this interpolation space and this interpolation couples. Okay, let's start with grand Lebesgue space. So grand Lebesgue space was introduced by Ewanik and Esberdon in 1992. On the left, this is Ewanik, and on the right, this is Esberdon, two Italian mathematicians. And they were considering some integrability properties of Jacobian. And their arise this function space, because we'll see later these functions are little worse than Lebesgue space, and so they were used to capture some results around this Jacobian. Then in 1997, Greco and with these two authors, they consider a generalization of this space called the grand Lebesgue space, but here they used this parameter theta, and this enhanced or enlarged the scope of this space. But the this was not generalization. This space was used to study p harmonic operator. I will show you this result. It's a very powerful result and one of the motivation to study these spaces. Okay, so let us start with Lebesgue function space. Usually it is called Lebesgue space, but I put this word function because you have Lebesgue sequence space. So this is the set of sequences, and then you have Lebesgue function space because it consists of purely functions. So if you have p between 1 and is infinity, you can take p equal to infinity as well, and omega is some measurable set, we say a function belong to this if this norm is finite. In fact, if you see the properties of norm, for example, this as a norm is non-negative. By Minkowski inequality, you get the triangle inequality. If you plug alpha here, you can take this guy alpha outside, and the properties are all there. And if you put G equal to 0, then the norm is 0. But there is a problem with this definition. The problem is, you know one definition of norm, that if the norm of some element is 0, if and only if that element is 0. But here it does not happen. For example, if you consider this function g of x, let us consider omega to be say 0, 1, and you consider this function 1 when x is say irrational in 0, 1, and 0 no 0 here and 1 here when x is rational. So this function, definitely this is not equal to 0, because at some point it is the value is 1. But if you try to calculate this norm, it will be 0. So you can find a function which is different from 0, but its norm is 0. So how this problem was tackled? This problem was tackled by introducing the equivalence class. We define this equivalence class that two functions f and g are related if and only if f is equal to g almost everywhere. From almost everywhere, we mean that for each point, f of x is equal to gx, but for the points x where f of x is not equal to g of x, the measure of that set is equal to 0. And because this set, the set of measure 0, if you go through this theory of Lebesgue integral, this set of measure 0 does not contribute anything to the integral. So if you have two functions which are almost everywhere equal, we have a very nice theorem that their integrals, their Lebesgue integrals, are equal. And that is how this function space was defined. They defined this equivalence relation. Based on this equivalence relation, they did the following. They did this quotient group. They classified this space using this relation, and then you have equivalence classes. The good thing about this characterization was the following, that no matter what element you pick from this equivalence class, you get the same integral. And in particular, you get the same norm. So, so you can define this space as a set of equivalence classes, but what practically you are doing, you can pick any function from the equivalence class. So the norm definition remains same, but the structural thing, you cover this thing by defining this quotient group. So here the 0 element refers to the 0 equivalence class. This means all the functions which are almost everywhere 0. For example, this guy is almost everywhere 0 because here it is not 0. And where it is not 0, on the set of rational number. The set of rational number, the Lebesgue measure of set of rational number is 0. So this is a very nice example to understand this one. So about the embeddings, if you have exponent p less than q and measure by modulus, we mean the measure of this set is finite, then LQ is contained in LP. So this space is decreasing with respect to the exponents. So this only happens when the measure of space is finite. This is important for us. So let us start with this grand Lebesgue space. So we have Lebesgue space. And now we want to see what is grand Lebesgue space. So by name, if you see grand Lebesgue space, grand means something larger. So we expect this space to be a bit larger than Lebesgue space. So we start with any subset of Rn whose measure is finite, and we pick P which is more than 1 and is finite. I will comment why this range is important. And we consider the measurable functions. And these functions belong to all LP minus epsilon, where epsilon is between 0 and P minus 1. So why this range is important? Because if you put epsilon equal to 0, you get LP. And when you put epsilon equal to P minus 1, you get L1, the largest space here. So if you consider a function which does not belong to LP, then by this definition, if the function belongs to LP, then this norm is finite. But if the function does not belong to LP, then this norm is infinity. So this guy blows up when f does not belong to LP. So if f does not belong to LP, but we consider the function to belong to LP minus epsilon, where epsilon is between 0 and P minus 1, then this function, this guy, this increases as epsilon goes to 0. Why this is happening? This is happening because of this relation. Because this space is, this space is decreasing. So when you pass the limit, epsilon goes to 0, this guy goes to LP. And if this norm goes to LP, we know that function does not belong to LP. So this goes to infinity. So this element goes to infinity. So there is a problem. Now, what this can be characterized by, for example, if F is in LP, then by Holder inequality, you can write this one. But to control this blow up, Greco, harmonic, they put some small parameter epsilon. Now this element is going to infinity, and you multiply this thing with a small parameter epsilon, which is between 0 and p minus 1, and you take the supremum. So when you take the supremum, then this controlling parameter now plays a part to make this norm finite. So this is what we call the grand Lebesgue space. So this grand Lebesgue space, let me put this one here. This grand Lebesgue space is larger than LP space because of this inequality. So why? Because of this inequality, we say that if A is embedded in B, if and only if norm of X, B is less or equal to norm of F, B. So you have, if you take the supremum, so you have LP, and because on the right hand you don't have any epsilon, so if you take the supremum, so it doesn't affect the right hand side, so you have this one. So this means if you look at this one, this means that LP is contained in LP grand. So this space is a larger space than LP, and as I see that I tell you that we are consider this space is interesting when the function is when the function does not belong to LP. So we are capturing some functions which are slightly outside the LP. So this was the motivation to write this space. And then they were also able to find this example that if you consider this function is here, but not here. So this is an example of a function which is in grand, but not in LP. So this inclusion is proper. So this was particularly used for this kind of function to deal this kind of function. So as I told you, the idea of putting this parameter epsilon here was to control this blow up. But you can put, for example, anything. For example, you can put epsilon theta. You can put a function, rho of epsilon. The only thing you require that this guy should go to 0 when epsilon goes to 0. So Greco in 97, they put this thing epsilon theta, and where theta is some positive number. Of course, this guy goes to 0 when epsilon goes to 0. But this factor had a part had a role to play, because this was used to solve to give some very strong result for p harmonic equation. This is the p harmonic equation, and I would like to tell you this result. If you can see, it says that if the function, this is Greco, if the function is here, and you can see this is theta, which was there, and theta is in this range, then p harmonic equation has exactly one solution in this Sobolev space. So this is a very powerful result which gives the existence of solutions in for this p harmonic equation, and this was not done for LP function. So for this particular p harmonic operator, this space was constructed. And after that, the things got interesting. It was 97, and see, first paper 92, then after 5 years 97, then people realize that okay, this as a function space is something very important, and then people try to study these spaces. So if you see the structural properties, they were first considered by an Italian mathematician, Alberto Fiorenza, and he had this uh, two very good research papers around these topics where they discuss this duality, the reflexivity, and in fact, this thing, small space, and is a kind of a dual of Grand-Lebesgue space. And it was also introduced by Fiorenza and Karazov. I was lucky to have Professor Karazov as my teacher when I was doing my PhD at Abdus Salam School of Mathematical Sciences. And I learned a lot from him around these spaces. So in fact, that was maybe 10 years ago. It was starting point to consider these spaces. Um, Later, when we talk about variable exponent, so what is Lebesgue space with variable exponent? We can do it here. For example, you have this space we define by this one. Why? How about this one? We replace p by a function of x. Then, for example, if you try to put it here, then it is not a norm. Why? Because now, if you try to compute, everything will depend on x. But the idea is clear. We want to replace p by some variable exponent. And this was, in fact, it is an old thing. It began in 1940 by Orlitz. But it was studied using this approach of modular function space. But there are many properties for variable Lebesgue space which does not hold for classical LP space. Maybe later, if I has chance, then I can give a very detailed talk about this variable exponent space and how it is used in harmonic analysis. So Alexander Maskey, he is my as a PhD advisor, and he was very much concentrated around this topic. And he was the first who considered the Grand-Lebesgue space with variable exponent. And then it was in 2014. And these guys, for example, Kokilashvili, Maskey, Raffero, Samko, apart from Samko, all of these three mathematicians are my co-authors. They have this series, integral operator in non-standard function space. By non-standard, we mean this variable exponent function space. This is volume 3, but they have, hello? Here they have 5 volumes around these non-standard function spaces. So they are very much concentrated around these topics, and they progress in direction in direction of Grand-Lebesgue spaces. So some drawbacks of this Grand-Lebesgue space is that the C0 infinity function are not dense in Grand-Lebesgue space. This space is not reflexive. However, Savano and Massey they obtained some result around this density and duality of this Grand-Lebesgue spaces. So that is why sometimes if you want to do some approximation results, it's very hard to do on these spaces. If you want to, seek further studies around these topics, then there is this nice survey article by Fiorenza, Formica, Gogatishvili, which tells you about this grand and small Lebesgue space and the Sobolev space. And they also connect this topic for the application in PDs and so on. Recently, I'm visiting Professor Suragan, and he has a very nice article on Hardy type inequalities in generalized Grand-Lebesgue space. As you know, this Hardy inequalities, they are connected with this Hardy potential, and these inequalities are very important if one wants to find these weak solutions for some PDEs. So the next problem was, if you see the starting point of Grand-Lebesgue space was that we start with a measure of omega is finite. Why? Because if measure of omega is not finite, then we don't know what happens here because we don't have embeddings. So there was uh, a natural question: what to do when measure of omega is infinity? Because this embedding does not hold in general. So Umar Khaziev was the first one to capture this idea, and in fact, this idea is to use some weight function in front of f, which depend on x as well as epsilon. And then this weight function can be written as multiple operator, where this ax was later called as grandizer in the literature. And this was the first attempt to consider these spaces, and this is how they defined it. But this space was weighted Grand Lebesgue space. But later, they have this very nice property that this LP is contained in Grand Lebesgue space for the set of infinite measure. But this was for the weighted case. Later, Samko and Umar Khaziev, they consider the definition of Grand Lebesgue space on a set of infinite measure, and this is in fact the definition here. For example, as I was telling you, we don't consider p equal to 1 in this range uh, uh, because if you plug p equal to 1, then this supremum collapses. If you plug p equal to 1, then this set is empty. The other thing is the case when p is equal to infinity. This is also not considered because if we consider that one, then we don't know the embeddings in general. So for infinite measure, uh, Umberto, Rafero, and Samko, they also consider Grand Lebesgue sequence space because, you know, for the sequence space, you work with sums, and the sums are indexed on the set of natural numbers or integers. So if you see the counting measure of these sets, these are infinite. So after the development of this Grand Lebesgue space on infinite measure, they consider this Grand Lebesgue sequence space. Also, these guys consider this case when p is equal to infinity, how this space, they call this as borderline case, and how this space behaves. And these are bunch of articles where I was telling you that you can put even some instead of epsilon theta, rho of epsilon, and then they try to obtain that okay, how the space can characterize this grand space. They call it fully measurable Grand Lebesgue space, and uh, um, such articles do exist in literature where they try to see these things. And these are some references. They have this local grand variable. And recently, what was our motivation to work around this grand net space was introduction of grand Lorentz space. This article appeared in Analysis and Mathematical Physics recently. So let us talk about the net space. And net space is uh, a space that was introduced by Aaron Sultanov. Um, and this space originated in 1998. And Alan Sultanov is a full member of National Academy of Sciences of Kazakhstan. And he introduced this space. And because he's an expert in Fourier analysis, so his motivation was to capture something around Fourier inequalities. But since I worked around these function space things, so my motivation was to see this as a function space and see how we can obtain the results on it. So the space is closely related to Lorentz space, and we'll see why and how we can start. So the idea is very simple. You have some domain omega subset of Rn, and M star be the collection of all subsets of Rn with finite positive measures. So this is we call net. So net is nothing like you call it topological net or something like that. This is a set subsets, collection of subsets with finite measure, and we fix it at a star. Now here is the thing. This thing is called the average function, and this is in fact the truncated average. So why this is average? Because you integrate the function and you then divide by its measure of the set. And why it is truncated? Because you take this measure is strictly greater than t. People sometimes do not notice the real thing here. Usually when we define these function spaces using integrals, we try to put modulus of f inside. But here, if you see, the modulus is outside. Why it could be important to put modulus inside or outside? Because since these spaces, his original motivation was to study these Fourier inequalities. So you have this Fourier series. This Fourier series have sines and cosines. These are oscillating functions. So if you put the modulus, you lose these oscillations. So his motivation to study these net spaces was to preserve those oscillation and to see how to obtain this estimate. Because I will tell you something when we define this space. So this is f bar, and this space is defined by this norm. So when q is equal to infinity, it is given by this function where f bar is average function. Of course, f could be non-negative, but f bar is always non-negative because you are taking supremum of non-negative quantity. But the key thing is you are putting this modulus outside. So this was introduced by Erlan Sultanov in 1998. And for example, this space lacks some algebraic structure. So when a space lacks some structure, then it gives you more flexibility. But on the other hand, you also lose some tools. For example, if you consider R and you consider the set of intervals, say n and minus n, this they don't need to be disjoint, minus n to n, then you have this sine function. It belongs to some net space, but if you take the modulus, it does not belong to net space. So these functions, this space is not invariant under this modulus. So this was one of the motivation that if you put the modulus, then the function blows up. So this space was used to preserve, these oscillations and, uh, to uh, have this structure kind of a thing. The other thing is the following, that there is no Holder inequality on these spaces. It's still an open problem, and people are trying to work in this direction. I also tried. I obtained some part, but still the associated space, the representation theorem, lot of open problems in this particular area. So then with Sergei Tikhonov. Professor Sergei Tikhonov is a senior researcher at CRM Spain, concentrated around Fourier analysis. They consider this net space defined with respect to general measures. This general measure is, instead of Lebesgue measure, if you put the measure mu, then you can define everything like this, but you have another space. But now you can put this counting measure to obtain this discrete net space or net sequence space and so on. So it was introduced in 2011, and they studied this boundedness of integral operators. So why net space for me is an interesting function space? Because I don't look at this space from the point of view of Fourier analysis. For me, what is important that what structure it has as a function space. So the first thing is that if you take all, all finitely measurable subsets, then this space is same as Lorentz space. So now you can see previously your space was dependent on this exponent P and Q. Now there is some geometry, some underlying structure here. So if you change the net, the space changes. That is why this space have don't have fixed dense subsets if you try to see. For example, if you choose this net, the net of all balls, then this space also coincide with some values with the Moore space. So if you change the net, you get a different space. So this space is interesting because it also depends on exponents as well as some underlying geometric structure. So this is why this space is quite an interesting space. Now we wanted to consider the grand net space. So the idea is simple. We want to construct you combine these two ideas, the grand Lebesgue space and the grand net space, and see can we recover something like grand Lorentz, which was introduced recently. So this is our recent work, which is available on archive if you want to look at. This is grand net space as an application to integral operator. This article is under. The first thing, if you see our grandization in Greco, they consider theta to be positive. Now we allow theta to be real number, so we extend this range as well. So we consider omega subset of Rn, and we assume that measure of omega is 1. You can consider omega measure of omega to be any finite number because always you can normalize by dividing with the measure of this set. So you can consider any finitely measurable subset, but for simplicity we consider this. And let we consider M to be the net, then the grand net space for theta positive is given by this, and for theta negative, instead of taking supremum, now this guy is here we were adding f plus epsilon, now we are doing minus epsilon. So this infimum comes because we want to control this blow up, and when q is equal to infinity, we have such definition. So when theta is equal to 0, if you consider this theta equal to 0, this guys is 1. And if you try to compute the supremum of this guy, this is t raised power 1 by p. And this is exactly the net space. So when theta is equal to 0, if you see, then you recover this one. Exactly. So the first thing is it generalizes the net space. The other thing that when theta is positive, then this net space is between these two intervals, these two spaces. So net space is between this negative index g minus theta and gn theta. So our first question, since I told you that the net space coincides with Lorentz space on if you consider this compact net. So our first question was this: does this grand Lorentz space coincide with our grand net space if we consider this compact nets? So this is the grand Lorentz space, and we were able to show that, for example, this space, if you consider all finitely measurable subset, then grand net coincides with grand Lorentz. And this comes because of this very nice relation for this compact nets. And because of this inequality, we can prove that these norms are equivalent. So this further, enhance the scope of this grand Lorentz spaces. The other thing we obtain when q is equal to infinity, we were able to compute these equivalence relations. And we would like to point out when theta is equal to 0, this again coincide with this net space as we mentioned. The other thing is such kind of relation we don't have, in classical grand spaces. The other thing is for other also when S is non-negative, then we can compute these kind of things. The idea is not so difficult. You have to just calculate the supremum and try to see what is happening there. Then we have the structural properties that if M1 is contained in M2, then this grand net space is here. Then we have this when you have relation with theta, what happens with grand net? When you have the relation with S, what happens here? And when you have the relation with both, what happens here? The other thing is, as I was speaking, that uh, to control the blow up, we need epsilon to be small. So what is important for us is when epsilon goes to 0. So this is reflected here that in the definition we take supremum between for epsilon between 0 and 1, but you can choose any delta less than 1. Still the supremum would be more or less equivalent with respect to some constant. So these two results emphasize the fact that for the definition of norm, what happens near 0 is much important because you're going to get this supremum near those points. And this is a very simple proof, and we can catch this proof. This is another result. This result, if I would like to say, see, if you consider these spaces, there are three parameters. This theta comes from grand, this P and Q, this comes from net. This P is sometimes referred as principal parameters. And why principal parameter? Because with respect to Q, embeddings and many other results. So this sometimes also called the dead parameter, the second one. So this one, this particular embedding tells you how this grandization parameter is related to the second parameter. So we have this kind of embedding for this result. This was our attempt to consider this Holder inequality. For example, I told you this, we don't have a Holder inequality for this net spaces. So what we were able to get on the right-hand side, we have something like Holder inequality because you have these things. The problem was that we were expecting to have something like this, F into G, but we cannot get it. However, we were able to see that if instead of F, we have F bar, G bar, then this inequality holds. So this is a kind of a Holder inequality, but the original or the one which we refer to, the classical Holder inequality, on the left-hand side, we have the multiplication F into G. So this is our attempt and to obtain some kind of an Holder inequality on these spaces. Now I will tell you about this interpolation result. This interpolation result is between two Banach function spaces, and we call this real interpolation method, and it comes because of this K functional. This was introduced by Peter. And if you consider x0, x1, they are compatible pair of Banach space, and their K functional is given by this one. And we say this space, this interpolation space, consists of all functions. This is x0, x1, consists of all functions of this type on which this norm is defined. And this particular space is called the interpolation space between x0 and x1. And this eta is between. This eta is this interpolating parameter, and this q is called what we call integrability parameter. So this eta, like if you see in numerical analysis, you have 2 points and you want to find the information between these 2 points. You consider this convex combination. Also, there is that theta is always between 0 and 1. Here, the same happens here. This is your interpolating parameter. So if you take x0 as this one and this one, then this interpolation space is embedded in this one. And this relation, these exponents are related by this, these exponents are related by this relation. So this is another thing. For example, we don't know about this reverse embedding, that is it equal or not. So there is a criteria for net spaces that for some net, this reverse hold. For example, for local nets, there is a thing we recently found that this hold. But in journal, the criteria for this reverse embeddings, we don't have any. At last, I would like to see this. I would like to tell you about the integral operators. So if you have a Banach space, then you have this associate space. In fact, for net spaces, we don't have the associate space, but for grand net, we were able to catch some kind of not for grand net, for grand Lorentz, we were able to catch the associate space. So our first attempt was to find some associate space for net space. We were not successful, but while doing this thing, we found that okay, if we choose compact net, then we go to grand Lorentz, and then still we can use this criteria. So this criteria was first proved by Nursultanov and Tikhonov for net spaces, and you consider this integral operator and which acts from any space X into this grand net space, and we say that the necessary and the sufficient condition for this operator to be bounded is this one. This is finite. When theta is equal to 0, this condition coincides with the conditions given by Tikhonov. The other thing is our conditions are finer because we have some logarithm term, and this improves the criterion, requires less, condition as compared to the net spaces. And as a corollary, if you consider the compact nets, then we were able to capture for the Lorentz space with the criteria for grand Lorentz spaces here. And this is some results which we recently finished. I would also like to tell you that apart from this grand net, I also consider this problem of problems on net space. So we have this results known as Hardy-Little-Sokolov inequality. This is about the boundedness of this fractional integral operator. And we were able to seek that we have this Hardy-Little-Sokolov inequality on some special nets. For example, for one-dimensional nets, for ball, for Cesaro type net spaces. And that work was recently published in a very good journal, Constructive Mathematical Analysis. So I'm progressing in this direction recently because this space lacks some fundamental properties. But then it's interesting. It's challenging to do some mathematics around this topic. So at the end, I would like to say thank you. And here is something by Professor Tao. And I would like to, tell to the students who sometimes, get frustrated that they are not understanding and they are not reaching somewhere. And I think that's it. You just try to spend some time on some subject, try to learn it. And after some time, you will learn that you start to enjoy that thing. You start to, see how to tackle this. This is how you do even research also, that you initially you know nothing, you try to do it, and then you say, okay, this part is hard. Okay, this we cannot do. And after some time, you are able to do some good things. So thank you very much. Uh, Thank you very much.
Thank you very much.
Thank you, Asad.
If there are
Thank you,
questions,
Professor.
I would be more than happy to answer.
Sir, thank you so very much for your precious time. If anybody has that question, he or she can ask, sir. If you don't mind, I have a haphazard sort of question. May I ask the question?
Mhm. Yes, yes. Please proceed.
Okay. When it comes to GLS, it has the computational difficulty that it makes the calculation complicated when it comes to coding. And most of the AI libraries, including the TensorFlow, also don't support
Mhm.
it well. So, what's the use of GLS, grand labeled space in AI and machine learning?
You are asking about the use of granular backspace in AI and machine learning.
Yes, sir.
In fact, um, to this state, uh, uh, one has considered these topics around this one. But uh, I can tell you something about this AI and machine learning, how the function space they can be used there. For example, what you do in this AI model, you want to approximate something. Am I right?
Yes, sir.
Okay. So this could be a function. And as I know, initially, there are some neural network type operator like controbase. There are another operators. It is known that if f is continuous, then you have some neural network operator that converts pointwise. And if the function is continuous everywhere in the interval, then that convergence is uniform. So it was the classical approach. Uh, I saw some people now studying to a larger class of functions. For example, there are people who study these approximation properties when f is not continuous, but function is in LP. The function in LP does not mean that function is continuous. Even recently, I saw something around all spaces. Uh, uh, I think recently there is some people who are even considering this, uh, we call it that mixed norm spaces. And people consider this convergence theorem that how these neural networks are obtained. There's a professor from Japan, I also cited here, Yoshihiro Sawano. If you type on Google density theorems for neural networks in variable exponent Lebesgue spaces, this article recently appeared in Mediterranean Mathematical Journal. And the idea is very simple that uh, you have a function, but now you want to approximate. Now, when you want to approximate, then you need a class of function. What is that suitable class of function that could approximate, some given function? And that given function could be any scenario or anything what you could imagine.
Okay, sir. Thanks a lot for your reply. So, it's the request to Sir Sohail Iqbal to please give his remarks on the session.
Ji, thank you very much, Dr. Asad. It was a wonderful talk. I'm sure some of the students understood some of the things, but all of us were kind of motivated from all these things. So thank you very much. So is there any question from the students?
Yes, sir, I have a question. Sir, as an undergrad student, how can we start preparing ourselves for the research in mathematics or any other field?
आपकी आप
I
क्वेश्चन रिपीट करें, आपकी आवाज नहीं आ रही थी.
I could not hear you.
तो मेरी आवाज आ रही है?
जी जी.
Okay, sir, मेरा question है कि sir, as undergrad student, how can we start preparing ourselves for research in mathematics?
For example, जब मैं undergrad student था, I'll give you this example. When I was undergrad student, I tried to read some books, and sometimes as a student, we read part of the book. When it comes to the exercise, we try to do some exercise and then leave it. I try to do those exercises and try to get to see some pattern. Okay, how I can do these things as well. As undergrad student, as you get into this last 4 semester, the first thing you should feel that where you are good at. You should feel the topics you like, and these topics shouldn't be the topics that everyone is doing. It should be your personal thing. Personal in the sense that you are interested in these topics, and then you try some resource person from your faculty who can speak with you, and you need some mentor to have a starting point. The first part of research is to understand some structure, whatever it is. You're working in applied mathematics, you try to understand the structure. You're working in pure mathematics, function analysis, some other place, you try to understand structure. Then the base thing would be that you start collecting some references. The ideal way to collect the references, if you're starting with one paper, go to a list of reference, try to download all those paper. The university, I'm sure the university does provide access to many journals, and you can get it. And then don't read all the papers. Try to read the first part of those papers and try to see, okay, what people are drawing. After some time, you will be able to join the dots. You will be able to find the research gaps. You will be because these topics you choose by yourself because of your interest. You will be able to feel that okay, these research gaps exist, and now you can maybe search these research gaps. Maybe someone already did it. If someone already did it, try to read them. Maybe there are some open questions there. And once you start doing this, after some time you get used to it, and it will make you to find the problems. And sometime after maybe a certain number of years, you will look at the paper and you have a problem already in mind. That is where you want to be at as a researcher.
Thank you, sir.
Okay, so असद जब आप नई फंक्शन स्पेसेस बनाते हैं तो कैसे पता चलता है कि कौन सी प्रॉपर्टीज को देखना है, कौन सी प्रिजर्व कर रही है? डू यू डू एग्जांपल्स और डू यू think general, or tell us about your motivation?
Yes. Okay. To be honest, when we start with function space, when we define some function space, our first motivation is purely theoretical. That, okay, we have certain function space and we want to see, okay, can we enlarge this space or not? Okay, first thing is purely theoretical, and we try to see, okay, does it have structural properties? Structural property, do we have this norm structure? Do we have these embeddings? Do we have, for example, Holder inequality? This is a very key tool in harmonic analysis, some other inequality. Then, once you are convinced that your definition is correct and everything is in line, then you try to find some examples. And this is the most difficult part, that when you try to find some examples, which is, shows that this space is different from another. Even if you don't find example, you shouldn't stop there. You should move on. You should see that, okay, if some theorems holds on this space, do these theorem require some new technique or not? If they require some new technique, definitely there is some new function space. If they run on the same plan, then maybe it's not maybe interesting. But if you can change, and if you see that some new methods is used, then maybe we cannot catch the example at this moment, which will take maybe more time. But if it is using some new methods, then this is always a good good hint that this space is different, and maybe you can spend maybe more time, and then you can seek these spaces. So that is what I told my students also. Always my student always try to ask me that, okay, why this function space? Why? Because what I had experience with the student, that they always want to jump from 1 to directly to maybe 99 or maybe 100. But I tell them, okay, the first thing is we should consider this theoretical aspects. Once we are convinced that, okay, everything is there, then we try to, connect with some known things and try to see one how it can be used. But for example, this function space thing, uh, always, maybe we are not expert around those topics, but always one way or the other, they will find these applications.
Okay, okay. So another kind of question which is asked to pure mathematicians most of the time. So what are the applications of these things? But of course, I'm not going to ask that. But how do you convince students about the motivation of these things? The students, undergrad students or MS students.
Well, the meaning of application is different for different person, but I know for undergrad student is quite different. When we say the word application, sometimes the natural meaning is to see some, to build something to be used in some applied problems, to some engineering thing. But for example, application of some theorem is to compute something. I can tell you, for example, uh, there is a very nice theorem in real analysis that if you have a continuous function on a closed interval, then it's bounded. So what is the application of this theorem? If you see a function which is continuous without doing anything, you say, okay, it's bounded. So this is another kind of applications. Some theorem, some results simplifies your computations, simplify your results. Maybe this result was used by some engineer, some guy who wanted to compute this, boundedness of this function. But if he knew that, okay, this function is continuous, he wouldn't do that. So the first thing is to seek applications of that result inside mathematics, and then this interdisciplinary approach will lead to the application in other branches of sciences. I can quote one example. I spoke about this variable Lebesgue spaces. It was first introduced in 1940, around this 1940 and 50, and it was purely theoretical. And then people try to see the structural properties and so on. And I think in 1992, after maybe 50 years, 40, 50 years, very few work was done around these spaces. In 1992, there was two mathematicians, Ruzicka and I'm forgetting the other guy. They had this monograph, uh, electrorheological properties of fluid, where they found these variable exponential spaces naturally arising in this problem. And then these guys thought that, okay, we found something new. And then they realized, no, this is 1940s. But those guys like Aldrich, these guys, they knew that this space would, maybe not today, maybe some year after, it will serve well. And if you see the trajectory of this variable exponential space after 1992, people are working around these topics. And I not only do this function space, I also do this mapping properties of singular integral operators. And if you talk about the integral operators, it is already some solution of some differential equation or related there. For example, if you want to go from differential equation to solution, what is the idea? You need to integrate, and when you integrate, then you end up with some integral operator. So this boundedness of integral operators tells you that, okay, this integral operator, which may be the solution, is in some function space. You already know where this function lies.
Okay, thank you, Asad. Thank you. I'm sure there are many other questions as well. Like I think it's time to end. Ji Bacho, over to you. Mohsin Raza. Ji Mohsin Raza, please ask.
Assalamu alaikum, Dr. Asad Zaighum. I have Dr. Mohsin Raza, Dean Faculty of Sciences, Northern University. I have a question not regarding today's topic. Okay, I have one question, but not related to today's topic, but I hope so. It is motivated question. How does a mathematician or a good mathematician become a good educationalist? I often find myself stuck when facing difficult decisions regarding academics, and your recommendation have always worked for me. My question is simple. Does mathematics help you in your administrative job?
Any kind of knowledge can help you in this task. For example, I can tell you very simple example. I got this position as chair of the department in 2020, and we had a huge flux of students and at our master's program. And since our infrastructure at Riphah International University was limited, we had to seek some solution to adjust our students. So we did a very simple thing, and it's purely based on this mathematics and this discrete mathematics. In fact, it was maybe 6 months before I was the chair of the department, and I told them, okay, our class timings are until 4. Let us increase until 6, 2 hours, and we have 20 rooms. You multiply 2 into 20, you have 40 hours. And this 40 hours is sufficient to accommodate one section. Of course, they cannot take this 40 hours at once. We need to, translate this timing slots where we use this discrete mathematics. And we can, always adjust. But, the simple things, I learned in this discrete logics how to, do this translation helped me when I was doing there. Maybe I'm forgetting many other ways I was able to, not the rigorous mathematics, but the simple and the tiny. This mathematics thing is in your mind, in your thinking. So when you seek to some problem, maybe it's not the concrete thing that you're going to apply, but these ideas, how your mind is developed, helps you to tackle that problem.
Thank you, Dr. Asad.
Well said, Dr. Asad. मेरे एक टीचर होते थे, प्रोफेसर कैसर, वो भी यही कहा करते थे, if you can do mathematics, you can do anything in the world.
Yes, of course. I strongly agree with this.
Ji Bacho, over to you.
Thank you so very much on the behalf of Siam for your precious time and for the detailed analysis on functional space. That's all from my side.
Thank you very much, and I'm happy to contribute this in this seminar of Professor titled with Professor Q.K. Ghori. Just at last, I would like to say some word for Professor Ghori. I still remember when he passed away. I think it was 2 weeks before some faculty members from COMSAT got some national prize. It was Dr. Aslam Noor and Dr. Salim Asghar. And we kind of invited them to celebrate at some in the university. I still remember, I think it was maybe 10 days before he passed away, but he was very kind to come and to give, serve as chief guest. And I remember that he would be there to, motivate the student in person, although maybe his health was not good at that moment. But as long as I was in COMSAT, whenever I see you, you could not feel that this person is so old. He is always active. And maybe sometimes I knew this postgraduate student, they say that professor is quite strict. But whenever, as undergrad student, we talked to him, he was very polite and very calm in this. So he was, I would like to say, one of most influential mathematician in Pakistan, and his contribution to start this mathematics culture cannot be compared to anyone. So I always remember him, although I did not have any course from him, but as a human being, he was one of the most gentle human being I have ever met. Thank you very much.
Thank you, Dr. Asad Zaighum. Thank you, students, for organizing this very wonderful and motivating talk. Thank you all. Goodbye. Allah
Thank you.
Hafiz.
Allah Hafiz.